Not that particular research. That research kind of just evaporated. I never went back to the chemistry class after the discussion of symmetry groups, because all of a sudden that was just, I have to do the lab work. I could look at a crystallographic structure and then three-dimensionalize it. Oh no, that's this. If I do that, I never went back to the hard science. I ended up teaching physics for 3 years, but I never ended up doing it in any real sense. And putting me in a lab is a bad thing. I tend to break stuff. One of the very first lab experiments that I actually did for the physics lab here was on accuracy and precision. I made them calculate pi. Here's a problem. Measure its radius, here's diameter, measure its circumference. Here's an orange. Measure its radius, measure its pi. Here's a blue. Same deal. Explain why your errors exist. Here's a meter stick and a pellet. Take a weight, drop it from a 2-meter height. Time how long it takes to get the pellet. Calculate gravity. Explain the sources of your error. Those 2 questions took 4 hours. The electricity and magnetism labs were more fun. We blew stuff up. Some of those labs are still done by Dr. Bogdan. Anyhow, that's lab sciences. We're doing calculus. Questions on 10.5 and 10.6 conic sections in Cartesian and polar coordinates. What questions do you have? At another appointment, he emailed me. Yes. 10.5, which one? 40. Do you want to do 39 or 41 in response? So 39 says the foci are at 0,2 and 0,6. And the vertices are at 0,0 and 0,8. Okay. First thing, let's draw a picture. So I have these 4 points given to me. 0,2 and 0,6 for the foci, and then 0,0 and 0,8 for the vertices. So far, so good? Okay. This means my ellipse is oriented vertically. So I know that the equation for my ellipse the bottoms are a squared and b squared. And a is larger than b, and a is under which of those two? I know that this ellipse is oriented vertically. I know that the equation has an a squared and a b squared on the bottom. A is bigger than b. So which one of those does the bigger number go under? Because that's the direction we're oriented. Yes. So this will be a squared. This will be b squared when a is bigger than b. Great. Wonderful. In order to figure out the four numbers that are in this equation, I need to go back to the picture and figure out what I can get from it. So, first question, where is the center of this ellipse? Say again?
0, 3.
Why 0, 3? Because it is in the middle of those two pairs, right? Halfway between 0 and 8 and halfway between 2 and 6 is 0, 4. So that is the center, HK. Great, I have two of the four numbers I need. Beautiful, wonderful. The other numbers, A and B and C, come from distances. C is not actually in the equation. Where does C come from? That's not true for an ellipse. That's true for a hyperbola. Because in a hyperbola, this is a minus, so we use a plus. In an ellipse, this is a plus, so we use a minus. In an ellipse, it's c squared is a squared minus b squared. Great. A, B, and C come from points on and related to my ellipse. Which of those numbers can I get from here? And what is A? How? Before you tell me what the number is, tell me how you're getting the number. From the vertex to the center. So this distance, that's A. How far is that? Okay, great. And notice that's the same whether I go down to the lower vertex or up to the upper vertex. There are two other points up there. What distance goes with them? Which one? That's an important question. What are these 2 points called? Oh, that's these two. See? They're the foci. Focus. Focus has the letter C in it. So this distance, that's C. And that is 2. B is across the ellipse. It goes the other way. That goes with the minor axis, which we don't have anything about here. So if I want to get B, I have to use A and C, and I have to use this. So B squared is 16 minus 4, that's 12. So I could take the square root of 12, which is a little bit bigger than 3, right? 3.4-ish. And I could draw that, but it doesn't ask me to draw. It just asks me for the equation, right? Well, now I have H and K and A and B, and I can put everything in here. The important thing to remember is which letters go with which pieces in my drawing. vertices go with A, foci go with C, the minor axis goes with B. And then I need to remember whether I'm using plus or minus here, and that's based on the opposite of what I'm using here. Better? Wonderful. More questions? Yes, sir.
I was kind of confused about the setup of
49. 49. Okay. Paraloon and apaloon, like perihelion and aphelion, are closest approach and furthest approach. But if we think about an ellipse, we've got to focus somewhere in there, right?
Yeah.
So notice where my two vertices are. There's one vertex that is very close to the focus, and there's another vertex that's very far from the focus. And it says rather specifically, in a lunar orbit, one of the foci is the center of the moon. So what I can say is, oh, the paraloon altitude is 110 kilometers, but that's above the surface of the moon, right? This distance is 110 kilometers. I've drawn this completely out of scale, yes? This distance is the apaloon, and that's 314 kilometers. But I also have to worry about the radius of the moon, right? But it gives me that. It tells me that the radius of the moon is 1,728 kilometers. So really, if the center of the moon is one of the foci, then I know this distance. I know this distance, right? That means I know where the foci and the vertices are in relation to one another. Means I know how big the major axis is, right? So I can figure out what the center is, and then I can figure out all of A and C and D from there. There's a spacecraft that is launched, I think, just in the last couple of weeks, called the Europa Clipper. And the Europa Clipper is going to do the same sort of orbit behavior around Europa, one of the moons of Jupiter. It should arrive in like 5 years. So this is a way off experiment. But here's the interesting part. Instead of orbiting around Europa this way, where sometimes it's behind Europa and sometimes it's in front of Europa, it's going to orbit Europa this way, relative to us, which means it will never go dark when it's hidden behind the back of Europa. We'll be able to talk to the Europa Clipper satellite because they're going to set the elliptical orbit up with Europa at a focus. They're going to set it up perpendicular to us. And they're going to use two different hyperbola to get there from here. Because in order to add energy to the satellite, once it leaves Earth orbit, they're not going to just keep thrusting all the way there. They have to carry too much fuel. So they're going to point the satellite at Mars. And they're going to miss Mars just a little. And they're going to traverse a hyperbola around Mars and use the gravitational force of Mars to throw energy into the satellite. Like if you go around a corner on a bicycle, you stick your arm out and grab on that push. It turns you really fast. Conservation of angular momentum based off of a conic section. It's everywhere, man. Most one and done comets or other interstellar objects like that, the cigar-shaped one, they called it Oumuamua or something like that, 6 or 7 years ago, travels a hyperbolic path through the solar system where the sun is at the focus of that hyperbola. Comets travel elliptical paths because they come back. Halley's Comet takes, 75, 76 years to go around its elliptical orbit. And the long end of it takes it well past Pluto. The close one takes it right up to the sun. Perihelion versus aphelion, like Paraloon versus Apollon. I grew up in Florida, not that far from the Space Center, so I did a lot of astronomy as a kid. Better? Yeah. All right, more questions. Yes, ma'am. Yes. The other vertex is just as far on the other side of the focus as this one is on this focus. So yes, I don't need that coordinate because I can deduce the information from this idea of symmetry. Oh yeah, absolutely. I promise you they give you enough information. They just hide some of it. Fun. Because I only really needed one vertex to get 7. I only need one pair. I either need the vertices or I need the foci, so I can split the difference. Did I tell you guys about whispering galleries on Monday? Oh, okay. Ellipses. The geometry part about ellipses is if you're standing at one focus and you send out a signal, whether it's light or sound, it bounces off the ellipse and lands at the other focus. So in DC, there is a beautiful statuary hall called the Whispering Gallery. And in the middle of this beautiful ellipsoidal room is a star on the floor. Way over there across the room is another star on the floor. And if you stand at one star and I stand at the other star, you can hear me, no matter what else is going on in the room. When this room was built in the late 40s and 50s, it was used for several international meetings. And the United States hosting those meetings made absolutely sure that they had a person standing at this star. And they sent the Soviet Union over there at the other one. So as all the Soviet diplomats talked to each other, we recorded it. And regardless of what else was being heard in the room, no matter how many people were talking or moving around, you could hear everything that happened at that desk, simply because you're at the other focus. There are lots of rooms with this shape. It's now called a whispering gallery in general. Take the same idea, shrink it down a bit, put it in a bathtub. Why a bathtub? Because bath water conducts sound really well, right? Take a sonic emitter, an ultrasound emitter, and put it at one focus. Put the person with the kidney stone at the other focus, and the ultrasound bounces off the wall and lands on the kidney stone and shatters it without ever going into the body. You don't have to do surgery to remove a kidney stone. It's called ultrasonic lithotripsy. They can break up a stone using sound waves and an ellipse. And that's a lot better than trying to go get a kidney stone the old-fashioned way, which involves putting a probe up there to get at the kidney stone, and that means going in through the only opening there. No, that's not fun. This is why I left biology. Those sorts of things made me twitch. More questions?
On 10.6.
28. Oh, the Hale-Bopp comet. So this is related to this idea here. We're actually trying to figure out how close we get. So we want to know if the sun is at one focus and we know the total distance across, where's the nearest side? So the sun is at one vertex. I'm sorry, the sun is at one focus. We're given the eccentricity, right? In polar, we got the eccentricity directly from the equation, right? But back in the Cartesian section, in section 10.5, there's another way to get E. And that is C over A. Wait a second. C is this distance, and A is this distance. They give me one other piece of information about this ellipse. What do they give me? And isn't that all the way across? So you know half of it, that'll give you A. Then when you know C, you can figure out how close we are. You're welcome. You will notice that Comet Hale-Bopp is a recently discovered comet, 30 years ago. It's not a long established, well-known celestial object. I was already teaching full-time by then. More questions? Yes, Maura. 30. Okay, so for comparison purposes, what other one do you want to do? 29, 28, 20? I don't know what the rest of them are in that section. Okay, so 28 gives me the equation. Y squared minus 2 equals x squared minus 2x. And the goal is to figure out what conic section this is. Okay, first thing I can deduce, this is not a parabola. Why do I know it's not a parabola? It's got two squares, right? Parabolas are either y squared in terms of x or x squared in terms of y, right? Two squares. So it's either an ellipse or a hyperbola. But that means everything should be on one side. So let's start with that. If I move it all over to the right-hand side, oh, I see an x squared minus a y squared. I am now pretty sure this is a hyperbola. So everything from here on out is completing the square. So that means I'm going to take that 2 and put it back over on the other side. What goes here to complete the square? I'm sorry? Okay, since this has a coefficient of 1, you take half the middle term and square it. So half of -2 is -1. Square that, you get +1. So the thing that goes here is a +1. But if I add 1 here, I need to add 1 there. And now this piece becomes x minus 1 squared. What do I get over here on the left? If I'm doing a hyperbola or an ellipse, doesn't that side need to be a +1? Multiply by -1. Or we could write it on the other side. Now, most of the time when I think of the equation of a hyperbola, there should be an over something, right? Like with an ellipse, there should be an over a squared and over b squared. So what can I put under each of those square terms to look like that? Fourth won't work in this case. I could just put over 1. And that means that A and B are the same, right? Well, that means that the asymptotes are y equals slope plus or minus 1. And they go through the point h and k. H is 1, k is 0. So through this point, with a slope of 1 and a slope of -1. It's always y number over x number. Now, the only other question I have is, which direction does this hyperbola go? Does it go up, down? Or does it go left, right? Y. Positive fraction is y, so the y part should be what goes up and down. As a matter of fact, this is where we can cheat, and we can go to the app on our calculator. Apps, conics, hyperbolas is number 3. Yeah, if the y is positive, we're going up and down. A is 1. We should go 1 unit up from our center. and 1 unit down from our center. Those are our vertices. And there's our hyperbola. Better? It's the slope is the number, the square root. It's the number under y over the number under x. So the slope is plus or minus 1 over 1. All of that is on that conic sections handout, including that rule, Jack, about the slope of the asymptotes. It's in the hyperbola section on that conic sections handout, which you won't have for the exam, but you can look over between now and then. Yes. A general statement. Every conic section, if I multiply it all out and I spread everything out, every conic section looks like if it's either along the x or along the y. If it's turned or twisted, like we were doing with our rotations, then I get something that looks like this. But since we weren't doing the rotated version, I was leaving out the B term. A lot of people go, why'd you go from A to C? Because that's really where that is. Here's the deal. All I have to look at are these two numbers. If A times C is 0, then you have a parabola. Because that means one of those two is 0 and you only have one square. If A times C is positive, then you have an ellipse. Because as you just said, Nora, they'll be on the same side and they have the same sign. So they're both plus or both minus, in which case they're on the other side and they're both plus. But if A times C is negative, then we have a hyperbola. So technically, I knew we had a hyperbola at the second line back here. One positive, one negative. Now, if you have B, this changes. And if you have B, then what you have to look at is you have to look at B squared minus 4AC. Gee, that looks familiar, doesn't it? And then we ask whether that's positive or negative or 0. But the conditions switch. If this is positive, we have a hyperbola. If this is negative, we have an ellipse. And if this is 0, we have a parabola. And once again, that's the same thing as comes from our quadratic formula, and it discriminates between our types of conic sections. That's why we call it a discriminant. And that's why I like rotating in polar, because it's a lot easier. Because doing the rotations to get that XY term is just way not fun. There's some linear algebra that will help you there, but it's not worth it. It's much easier to do it cold. More questions? I have no reason to keep you all nailed to the chairs here. If you've run out of questions, bring this stuff in tomorrow and I'll see you then. Right? Have a wonderful rest of your day. Yeah, I know, 10 minutes early. Write it down. Miracles occur. But if somebody wants to stay and ask me a question, you can stay and ask me a question. I'll keep the recording. But if you don't have any other questions, get out of here. I got nowhere else to be till 2 o'clock. But that's up to you guys. No, I promise it's not a trap. I don't keep track. Ooh, these people left early. No, but I can do 9 or 11. Which one do you want to see? Okay, so in 11, it's 2 over 3 plus 3 sine theta. So the first thing I need to figure out is what the eccentricity is, so I can tell you what kind of conic section we have. In order to find the eccentricity, what do I have to change? The standard formula looks like that. That means that that first number in the bottom has to be a 1. And right now it's a 3. So I'm going to divide everything by 3. That's the same equation. But now I recognize what E is. What is E? The number in front of sine theta, which is a 1. Okay. When E is 1, what kind of a conic do I have? That's parts 1 and 2. Part C says, give an equation of the directrix. The directrix comes from D. What's the value of D? Because the top of my fraction in standard form is E times D. But that's just a number, and the directrix is a line. So it's either x equals or y equals, and the question is, which is it? Because, correct. The only other question is, should I use positive 2/3 or negative 2/3? Because the positive with the sine theta, that is exactly correct. Which means the focus is here at the origin. In every polar conic section, the focus is at the origin, a focus is at the origin. And this is a positive number. This curve should go like this. And since part D says sketch a picture, out comes my calculator, and I can actually graph this. I'm in polar, so 2 divided by 3 plus 3 sine theta. Poof. Lo and behold. And it's kind of hard to see, but it just does barely come up above the axis. As a matter of fact, if you hit trace, you'll see that we are at a height of 1/3, halfway between the focus and the directrix. 2/3 of the focus is at 0. There we are at 1/3.
Yesterday, whenever is something is parabola or something.
Okay. It's a parabola when E is 1. If E is bigger than 1, we have a hyperbola. And if E is smaller than 1, we have an ellipse. As a matter of fact, 1 being the dividing line shows up really nicely some of the illustrations I stole from another book. This is from the trig book. So all the way on the left, we have an ellipse whose eccentricity is 0.5. That looks pretty close to a circle, doesn't it? And as we go further to the right, as we get closer to 1, our ellipse gets longer and longer and longer. When our ellipse eccentricity is 1, we don't have an ellipse anymore, we have a parabola. And then when we get bigger than 1, we have a hyperbola. In a sense, you could think of taking your ellipse and stretching it. And as you get closer and closer to 1, this side goes further and further away, so it's off infinity, you have a parabola. But then when you're bigger than 1, it shows up on the other side. We kind of wrap around infinity. There's a really nice picture. If you draw an ellipse on a sphere, you can actually wrap that ellipse around and see it cross over itself. So take a picture of an ellipse, put it on a tube, and as the tube gets smaller, back sides of the ellipse cross, looks like that vertical. Yeah, so that is my delineation. Oh, you heard of it. In polar or in Cartesian? Okay. There is no of A and C on a Cartesian equation for a parabola. The equation for a parabola is so really all I have to find is this one number p. And p is the distance from the vertex to the focus or from the directrix to the vertex. Since there's only one distance involved, we just call it p instead of a, c, whatever, right? So if I have a shifted one, the same thing still holds, only we're at h and k for a center, and then that's where our vertex is. And then you have to decide, are you going up and down, or are you going left and right? But then the distance in question is p. It's either p up, p down, p left, or p right from the vertex to the focus. A and C, there ain't no such thing as that. Hyperbola has A and C because the hyperbola's equation is the hyperbola has A and B, so it's going to have C. Just like the ellipse. Hyperbolas and ellipses are almost the same. The difference is the sign in the middle being plus or minus. Ellipse is plus, hyperbola is minus. Because an ellipse is a circle. It's been stretched by a different number, A or B, rather than a radius